Thank you very much. And then we kind of move over to our next presentation about SYNGAP and Sleep by Connie Smith-Hicks. Perfect.
Good morning, and it's great to be here. Thanks for inviting me. As you know, I'll be talking about sleep and SYNGAP. Let's see if we can move this. Oh. So my talk is divided into two parts. The first, I'm just going to give a background and an update of where we are in our knowledge, at least as it's been published related to sleep and SYNGAP. And then the second half, I'll be talking about some work that we have been doing, looking at both quality and quantity of sleep in this population. And the second half of the work is not yet published, and we're hoping to submit sometime next week. Next slide. So why study sleep? Well, we all know that sleep is critical for many physiologic processes, and for many of us who are neuroscientists, neurologists here in the room, we know that sleep is very important in neurogenesis and in plasticity mechanisms. Both parents and individuals who have had sleep problems recognize that poor sleep has adverse impact on the quality of life. It can negatively impact attention, learning, memory, mood, and behavior. Sleep problems are very common in the pediatric population, and we see in typical developed kids, 20 to 40% of them are reported to have sleep problems. But in individuals with neurodevelopmental disabilities, anywhere between 40 and 80% have been reported to have sleep problems. And sleep problems in this population manifest with insomnia, so difficulty with sleep onset or sleep maintenance, sleep disordered breathing, as in sleep apnea, resulting in increased daytime sleepiness. We heard some mention to that earlier. The sleep challenges that we see in children with neurodevelopmental disabilities tend to be more severe in their impact as compared to individuals with typical development. I think there's been at least 3 or 4 references to the work by Ingrid, which you'll see on the left of my slide. And she led a team that nicely characterized the clinical features or phenotypes of SYNGAP1. I have circled or identified the group that have sleep problems. It's reported to occur in about 62% of the individuals in her study. About 53 are reported to have autism, 53%, and about 85% are reported to have epilepsy. Now, sleep problems are common in children with epilepsy, as shown in this meta-analysis that I referenced. And the nature of the sleep problems in the patients that were examined are reduced sleep time and reduced sleep efficiency. There's increased parasomnias, night waking, and sleep disordered breathing. However, in a nice study out of CHOP looking at sleep behaviors in children with autism, they identified insomnia as the primary sleep difficulties in that population, manifesting with difficulties with sleep onset type. We know from work in rodents that SYNGAP is very important for sleep. The SYNGAP protein is expressed in the chiasmatic nucleus, and it regulates circadian locomotor activity and light entrainment. So for next slide. So for that reason and the clinical features that we've described, I collaborated with Jimmy Holder and Andy Stanfield to evaluate sleep features in children with SYNGAP. And in this particular study, I think we published it last year, we did a comparison with kids with SHANK3 or Phelan-McDermott, as well as typically developed siblings. We used the Children's Sleep Habits Questionnaire, which is a parent-reported screening measure. It allows us to assess behavioral and medical-based sleep problems. It was validated in children between the ages of 4 and 10 years old. However, this measure has been used in populations of individuals with neurodevelopmental disabilities into the young adulthood. when an individual has a score of 41 or greater, that is correlates with clinical significance. In addition to the total score, there are 8 subscales that looks at the different clinical features of sleep. So we have bedtime resistance, sleep onset delay, duration, anxiety, sleep awakenings, parasomnia, sleep disordered breathing, and daytime sleepiness. And in our work that was published last year, we show that individuals with SYNGAP1, when compared to their typical developed peers, had elevated sleep scores across all domains. So that prompted the questions that I'm going to tackle today, which are, were there predominant subscales that drives sleep problem in SYNGAP? I shared earlier that individuals with autism and epilepsy tend to have relatively high predominance of sleep problems. So the follow-up question would be, do kids with SYNGAP and autism have a higher burden of sleep disorder when compared to kids with SYNGAP but without autism? And then I hope to share some data we have with regard to actigraphy and correlates with the CHSQ. So the remainder of this talk, I'll be describing the children who were recruited through our center, the Kennedy Krieger Institute, 21 of whom completed the sleep history questionnaire. 6 completed the actigraphy, so the 6 of the 21. And their ages ranged from 3 to 17 with a mean of 8. They're about equal in male, female, 76% had epilepsy, 62% had ASD as diagnosed clinically and reported by parents. 81% of these kiddos were on medications, at least one med that impacted sleep. And you'll see that I divided them up into sleep aids, so primary sleep aids, as well as epilepsy medicines that can impact sleep, and medications that are primarily used for behavioral, but also impact sleep. So the first question we asked was, is there any difference in the total and subscale scores for all 3 groups? So the group of 64 patients published last year, and then the 2 cohorts in this study, and you can see that there's no significant difference. And then we next looked at the total sleep disturbance score and asked, are there any correlations? So what are the drivers of the subscale that's driving the sleep disturbance? And you'll see here that we have significant positive correlations with bedtime resistance, parasomnias, nighttime awakenings, and sleep anxiety. However, bedtime resistance and parasomnias had a greater impact than, say, nighttime awakening and sleep anxiety. The next question we asked was, is there a difference in those with autism and SYNGAP compared to those without? We had 62% had a co-occurring diagnosis of autism. And in the autism cohort, there's a greater preponderance of epilepsy and sleep-reported disorders. But despite that, there was no difference in the total or subscale scores for sleep parameters, suggesting that perhaps it's not the autism that's driving the sleep challenges in SYNGAP, but primarily the genetics of the SYNGAP biology itself. But in anticipation of the question, well, you know, it's really challenging to make a diagnosis of autism in individuals with intellectual disabilities. We used the social responsiveness scale 2, which is a well-validated measure, a parent-reported questionnaire that looks at social interaction and repetitive restricted behaviors. These are core features of autism, to sort of ask that question a little differently. And here we show that the total raw SRS2 scores positively correlates with nighttime awakenings. And that positive correlation is driven by the social communication aspect of the SRS2, as there was no correlation with the repetitive restricted behaviors. That's okay. And the SRS2 score is driven by the communication, so the social communication component of the social interaction domain, of which there are 4. So there is social awareness, motivation, social communication, and there's another that I'm forgetting, but we can move to the next slide. All right, so here I want to talk a little bit about some of the work we have done looking at the quantitative nature of sleep in SYNGAP. So we've used the ActiveWatch 2, which is a Philips Respironic device. It has an accelerometer that records motion. And some of the drawbacks of the ActiveWatch is that, or actigraphy devices in general, is that they do not measure the neurophysiological correlates of sleep. Restlessness can sometimes be interpreted as wakefulness, and quiet rest may be misinterpreted as sleep. However, the device is convenient, it's sensitive, it's non-invasive. An individual can wear 24/7 in their natural environment. And another positive is that the algorithm used to quantify and detect sleep has been validated against the gold standard, which is the polysomnograph. So in our study, we used a published control sample from the CHOP clinic, where they had 37 children from the community. These were well validated. They were screened for autism and other NDDs. The kiddos were between 4 and 10 years old, and 12.5% of them were reported to have some sleep problems. Of note, none of these kids were on sleep medicines. So we compared time in bed, sleep latency, total sleep time, sleep efficiency, and wake after sleep onset. And we were surprised to note that the controls had elevated or worse scores in sleep latency and wake after sleep onset. One possible explanation is that many kiddos with NDDs are either on medicines to help with sleep onset, but also parents are very experienced in developing appropriate sleep hygiene that helps to mitigate some of these challenges. Next slide, please. We were curious to know, given that our previous analyses showed no worsening for the kids with SYNGAP1 when compared to typical developed peers, how do we explain the findings on our sleep history questionnaire, where we see that sleep disorder is driven by bedtime resistance, sleep duration, and sleep anxiety in this cohort of kids who wore the actigraphy? So we did a minute level activity count using an ARC tools, which is a program in R. And we were able to look at 4 6-hour epochs, which you can see on the right of the slide. Notably, the total activity count from midnight to 6 a.m. and that period sort of correlates with the time when kiddos were asleep, as documented by their sleep log. That period correlates with sleep, and there is a significant reduction in total activity during that period of time. So to the top of this slide, you see 2 examples of actigraphy data. One from a child who has some activity during the midnight to 6 a.m. period, and the other with very reduced activity. So this sort of captures the variability that we see across all 6 participants. And the variability in total activity is driven by the number of minutes that they were active and not by the duration of the period that they were active. So we asked the question, are there any correlations between the duration of period or the length of the period that they're active during this sleep as compared to the CHSQ? And what we were able to identify is that there's strong positive correlations with duration of wake, with the total sleep disturbance, bedtime resistance, and nighttime awakening. There was positive correlation with sleep anxiety, but it didn't quite meet significance. So I want to wrap up and just talk about some of the takeaways from this. Sleep is common in children with ASD and epilepsy. Sleep is very common in kids with SYNGAP. Yet despite that, we saw no difference in CHSQ scores between kids with SYNGAP and ASD as compared to those without. That suggests that the sleep difficulties are being driven by the role of SYNGAP, the gene, in sleep. We believe that the CHSQ, despite being a parent-reported measure, is a useful tool for evaluating sleep. The sleep difficulties manifesting with bedtime resistance, parasomnias, night awakenings, and sleep anxiety seems to be the drivers of sleep disturbances in this population. And there are a number of sleep difficulties that are captured with sleep parasomnia terms. There is night walking, there's talking, there is teeth grinding, and bedwetting are some of the ones that are captured in the CSHQ. In our cohort, bedwetting was the most common. And then the duration of the wake bouts seems to be the driver of sleep disturbance in kiddos with SYNGAP. So with that, I would like to acknowledge certainly the families and children who participated in the study. My colleagues at Kennedy, Valerie and Ida were the two who worked on this study. Our collaborators, Jimmy and Andy, certainly bridged the gap in SYNGAP. They supported us in the recruitment and funding from Kennedy and Hopkins IDDRC. So with that, I'll take questions.
Thanks, Connie. That was really interesting. Two questions. One is, with the children with the sleep disturbance, was there a sense of any particular drug being most helpful, because families are exhausted and it's really important? The second question, the people on my left might be the better people to help, but I just want to raise it. Is there anything about the neurobiology of SYNGAP1 that makes sleep likely to implicate sleep? So I hand the microphone laterally while you have a go.
So regarding the question, medications, so many of these kiddos are on melatonin in addition to seizure medicines. And so melatonin is often used to target the difficulties with sleep onset. In looking at the actigraphy data, we realized that when parents said that they put their kids down to sleep, that is really when sleep began. So the suggestion is that perhaps melatonin is quite beneficial in reducing the latency to sleep. With regard to the issue of nighttime arousal, not quite clear on what, if any, of the agents are better able to keep kids asleep once they've awoken. With regard to the second question, so the biology of SYNGAP1 and how that might, that's a tricky one, because many of these kids also have epilepsy, and we know that there is this very intricate dance between seizures and sleep. So the short answer to that question is no, I don't have a handle on the biology, but it's certainly very interesting.
Yeah, I would just add that so SYNGAP gene and the proteins expressed in areas of the brain that mediate circadian rhythm. So that's consistent with the genetic, that's what Connie was referring to. And then we have some unpublished data in collaboration with somebody else where, we had seen these sleep disturbances in the animal models that were similar to what the Kadam lab published recently. And actually, interestingly, we found that those sleep issues could be reversed when we re-express this gene just in the cortex, which was surprising. We thought it would be from these lower areas of the brain that initiate sleep-wake transitions. And so in some data I'll show you in about an hour and a half, all of this makes me think that sleep is just one of the outcomes of the encephalopathy. It's a common disturbance that sleep is one outcome, autism is an outcome. And of course,
One more question.
Okay.
Do you have a plan to follow up with those patients over time? And I have a 21-year-old and his sleep was really terrible. It's gone through many phases, so it's a little better now. It's a lot better now.
Absolutely. So the plan is to expand the number of individuals with actigraphy, but also to follow them over time. Not just the actigraphy, but also with the sleep history questionnaire. And, some of the other questions would be, how does actigraphy data sort of correlate with some of the neurophysiological changes that we see in EEG and sleep? Thank you.
Thank you.